Today I thought of discussing the past paper questions from electronics, right? And now I'm going to start off with diodes, semiconductor diodes, right? And in the other videos that I'm going to publish, the other parts will also roll up, right? In the next days. All right, then let me share the screen. All these questions are taken from past papers, so they are pay-through questions, right? So you also can refer your own questions if needed, right? Almost all of you have the pay-through questions with you know. So these are the pay-through questions, right? Okay, we'll start with diodes. We'll start with diodes. Right, first one. Uh, Consider the following statements regarding an intrinsic semiconductors. What are intrinsic semiconductors? Intrinsic means they are pure. Pure means they are not doped or not mixed with other elements, right? If a semiconductor is mixed with other elements, they are called extrinsic semiconductors, right? If that is not mixed with other elements, that is called intrinsic semiconductors, right? Extrinsic and intrinsic. Okay, first one. The electrical conductivity decreases with increasing temperature. The electrical conductivity decreases with increasing temperature. Electrical conductivity decreases with increasing temperature? No, because in electricity, actually, we draw the variations of semiconductors, right? In electricity, we draw the variations of semiconductors. One second. Right. In electricity, we draw the variations of semiconductors, no? Right? So there, this is what we draw for a semiconductor, right? For resistance and resistivity of a semiconductor, right? This is how it varies over time, right? Resistance decreases a bit, then conductivity increases. So first one is wrong. The electrical conductivity decreases. No. When temperature increases, conductivity also increases. Conductivity increases because resistance decreases, conductivity increases. Then the ratio of the number of free electrons to the number of holes, not balls, holes, remains constant with the increase in temperature. That is correct. That is correct because by increasing the temperature, number of electrons or number of holes cannot be changed, right? Actually, the ratio. Number of electrons increases, number of ionized electrons increases, then simultaneously, number of holes also increases. Then the ratio remains unchanged, right? It says ratio, no? Ratio remains unchanged. Ratio remains unchanged. The actual number, it increases. That is true. Actual number of electrons increases. But the ratio is same. See, both the free electrons and holes contribute to the electric conduction process. Yes, that is true. That is true. Right? Both electrons are electrons and holes contributing. That's why we call they are carriers. Right? When it comes to doped conductors, we have majority carriers and minority carriers. Right? If there is not doped intrinsic, then we have carriers. Right? Both carriers are equal. Both carriers are equal. Then B and C are correct. Only B and C, it's 4. Only B and C, it's 4. Right? Second one. Which of the following graphs best represents the relationship between voltage and time for the output from a power supply consisting of an alternative current generating a full wave rectifier without smoothing? Right. That's completely taken from the theories, right? Full wave rectifier without smoothing. In full wave rectifier, right? All the wave is rectified, all the wave is utilized, right? Now, for a rectifier circuit, input wave is something like this, no? Because that's a alternative current. Then VAC is something like this, right? In the rectifier, right? What is done is, in a full wave rectifier, right? V out is, all these are rectified. All these are rectified to a single direction, single polarity, V out. And if there is what we call the smooth, then what happens is, from this peak point to this point, it will be connected, right? This is called the smoothing process. This is called the smoothing process. Now, in this case, if there is not smooth, that is 3. Right? If there is not smooth, that is 3. Third one. Which of the following combinations of resistance and diode produces the least resistance across the points X and Y? Okay. For this kind of a question, the theory part is this. If a diode is forward biased, right? If a diode is forward biased, its resistance is very small. So we assume it as 0. when it comes to calculations, right? If a diode is reverse biased, resistance is very high. For calculations, we assume it as infinity. Right? So that's how it changes. Okay, then the other thing to check whether diode is forward or reverse, right? What you need to check is if P to P, positive to positive of a diode is connected, that is forward biased. Right? Forward means, right? P to P and N to N should be connected. Reverse means P to N should be connected, right? Reverse can P to N should be connected. Right. I was explaining about question 3. Right? So about resistance question using diodes, right? These are the theory parts. If a diode is forward biased, R is very less, so we consider it as zero, approximately zero when it comes to calculations. And when a diode is reverse biased, R is very high, so we consider it as infinite for calculations. And to identify a forward bias diode, we have to check the connections. They should be P to P and N to N connections, right? If there is a reverse bias diode, P to N connections, right? And P of a diode is the triangular side like this, and N of the diode, negative side of the negative terminal of the diode is the dash, the side with the dash like this. And the diode is drawn plus and minus. Okay, now go to the first one. N to N, P to P connected. Now this is reverse biased, no? Right? This is reverse biased. If this is reverse biased, resistance is infinity. Right? If you are simplifying the resistance from scratch, right? What you can do is you can simplify this as 1 over 10 plus 1 over infinity. 1 over infinity is 0. Then this becomes 10. Then 10, 15, 10, 5 means this is 15. So likewise, you can simplify the resistance. Right? Right? I'm putting the answers at once by simplifying by mind. Right? If you are simplifying by the scratch, from the scratch, right? So you can simplify them as the traditional way, as series and parallel resistors. That's it. As series and parallel resistors. That's it. Right? Simple as that. Second one, P to N are connected, no, which means reverse bias. If this is infinity, then no current flows in the circuit. Total resistance is infinity. Right? In the third case, P to P connected, this is forward bias. Resistance is 0. Right? If there is 0, 10 and 5 means, right, 1 over 10 plus 1 over 5, 10 over 3. Then fourth one, N to N, this is forward biased. Then resistance is 0. If resistance is 0, 1 over 10 plus 1 over 0, 1 over 0 is infinity. Then 1 over R becomes infinity, so R is 0. Right? R is 0. Then total resistance here becomes 5 kilo ohms. 5. Right? And about the fifth one, that is again forward biased. Forward bias means is 0. Then the total resistance of the circuit is 10. Right? Then what is the question? Least resistance is 10 over 3, no? 3.3 something. So the answer is 3. Right? Answer is 3. For 3, answer 3. Right? 4. The variation of the electric field intensity E across an ideal PN junction is best represented by. Right. So we know in a PN junction, we have a depletion region. In the depletion region, or across the depletion region, it's a constant electric field generated. That's a constant electric field. Right. So we know E equals delta V over D. Right. From electric fields, E equals delta V over D. Right. Now delta V of a PN junction is voltage barrier. We call it the voltage barrier, VB, voltage barrier. Voltage barrier is a constant for a material. Now, as an example, for silicon, voltage barrier is 0.7. For germanium, 0.3. Likewise. And D is also constant, which means E is going to be constant. Right? Since E is constant, right? Very straightforward. Answer is 3. Answer 3. 5. Consider the following statements made about PN junction. Right? Its current voltage characteristic is linear. No, PN junction is not a ohmic conductor. Vi becomes linear if a conductor is ohmic. Right? If a conductor is ohmic only. So A is wrong because there is not an ohmic conductor. B. Built-in electric field across the junction is directed from N region to P region. That is correct. That's a good one. How to check it? We know we know when a PN junction is made, right? When a PN junction is made, right? So this is PN. When a PN junction is made, electron hole pairs are rearranged, right? Now in this side, P means we have holes, right? This side N means, right? This side we have electrons. This side we have electrons, negative, right? But when the PN junction is connected, right? The electrons and hole pairs which are in the close proximity to the joint are always reorganized or rearranged. Then what happens is these positives are going to this side like this plus, and minus are coming to here minus. They are switched. Right? This is what we call the depletion region. So in the depletion region, right, plus is here, minus is here. Then electric field is generated from plus to minus. Depletion region is the one who generates the electric field. No? So the ray is generated from plus to minus. Then as an overall, the direction is N to B. From N to B, so B is correct. Right, B is a correct statement. Second, B is a correct statement. See, current carried by holes and electrons are in opposite directions. No, they are in same directions because direction of current is towards the direction of holes and opposite to direction of electrons. Both are same. Then opposite wrong. Then only B is correct here. 1. Only B is correct. 1. Right? Only B is correct. That is 1. 6. Which of the following circuits draws the largest current from the 6-volt cell? Right. Similar to question 4 we did. Largest current means minimum resistance, no? Right? Higher the I, lower the resistance. Largest current is when resistance is minimum. Then check the one with the minimum resistance. Right? Check the one with the minimum resistance. Right? Since I explained the previous one a bit, I'm not going to explain this one again. Right? Check the forward bias and reverse biasness. And in this case, see, this is forward bias, R becomes 0. Then 1 and 2 are parallel, which means the resistance here is going to be 2/3. That's a minimum. Right, check resistance again 2/3. Right? Now first check reverse bias. Resistance is 3. Right? Resistance is 3. Second one, that is reverse bias, resistance is infinity. Right? Third forward bias, resistance is 2. Fourth one is also forward bias, resistance is 1. Fifth one is forward bias, then equivalent is 2/3. Right? Less than 1, no? 0.6. The answer is 0.6. Right? 7. Right, 7 is a good question. See, IA characteristic of the silicon diodes shown in the circuit A is given in figure B. 6-volt cell is negligible internal resistance of I1, I2, and I3. The maximum and minimum currents respectively are. Okay. Then about the diode, its IV characteristic curve is given, which means now this is actually 2 volts. Now there's a printing mistake in this particular question. In the original paper, if you check again, that is actually at 2. So I'm going to assume that as 2. Right? I took these questions from page row, but there's a small mistake in that graph. Right? In the original paper, it was at 2. So this is the reverse breakdown voltage. Right? This is the reverse breakdown voltage of this diode. That is 2 volts. No? Reverse breakdown voltage is 2 volts. Now when this diode is reverse biased, at a reverse breakdown voltage, probably this should be a Zener diode. Probably. Right? But probably this should be a Zener diode. Right. Now we know this is 6 volts. If this is 6, it says, okay. And about one more thing about its forward biasness. Forward bias voltage barrier is here, right? That is close to 1. Right? Forward bias voltage barrier is close to 1. Then this diode is forward bias, no? Then this keeps 1 volt across it when it is forward bias. This diode is reverse bias, then it keeps its reverse bias voltage 2 volts across it when it is forward biased. Okay, then we can find I1, I2, I3 by applying delta V equals IR for these resistors. So we know delta V equals IR. Then I is given by delta VOR, no? Right? Apply this for these 3 cases, for these 3 what we call the resistors. Then for the first one, delta V, from total 6, 1 is with the diode. No? If 1 is with the diode, the remaining 5 is across the resistor. Then 5 over R. Second one, if you need I2, right, across I2, total 6 volts is across these 2 points. Then 6 over 2R is 3 over, no? 3 over R. Then about I3, if 2 volts are here, remaining 4 volts should be here, right? Remaining 4 volts should be here. Then that is 4 over R. Then what's the minimum? Minimum is I2, maximum is I1. Maximum is I1. Then I1 and I2, it's 3, right? I1 and I2, it is 3. 8. The breakdown voltage of diode of the circuit shown is 5 volts. Okay. If the internal resistance of the cell is negligible, when the value of R is changed from 25 to 0, the current I in the circuit change from. Okay. Then first we will check when 25 ohms. So we know when diode is working, it keeps this voltage 5 volts across the diode, which means across this 50 ohms also that is 5 volts. From 10, the remaining 5 is going to be across this part of the circuit, no? Remaining 5 is going to be across this part of the circuit. Right? Then if you need I, right? Again, delta V equals IR. So I is given by delta V over R. Right? Then when this is 25, if you check this, right? Delta V is 5 and the resistance is R is also 25. This 25 is they are in series combination, then altogether that is 50. Then 5 over 50 means that is 0.1. Right? When there is 0, resistance becomes 25. Then that is 5 over 25. 5 over 25 is 0.02. Right? Sorry, 0.2. 0.2. Then 0.1 to 0.2. Right? That's an easy one if you understood the question, if you got the question. 9. The diode in the circuit shown has 0 forward bias resistance and reverse breakdown voltage of 75 volts. Okay, 0 forward bias resistance, which means no voltage barrier. That's an ideal diode. Internal resistance of the cell is negligible. The voltmeter reads 12 volts when the terminals of the diode are reversed. The voltmeter reads 12 volts. Initially it reads 12 volts. When the terminals of the diode are reversed, the voltmeter reading is. Okay. Now, in the initial state, right? Initially, if you check it, right, there's no potential difference here. If there's no potential difference across the diode, right, these points are same, no? If this is X, this is also X, Y, Y. Then 2 and 2 are in a parallel combination. They are connected across same points. Then initially 2 means 1 parallel 2 means 1. Then in the circuit we have 2 resistors of 2 ohms and 1 ohms in a series combination, and it reads 12 volts across 2 ohms. Then we can find the total potential here. Let's say this total potential is E, right? Now what we have got is something like this, right? Here 2 ohms, this is 1 ohm, and across this you got 12 volts. Then apply potential divider. 12 equals total over addition of resistors 2 plus 1 times 2 is 12. Right? Then what about E? Then E becomes 18 volts. Then total of the battery is 18. Right? Now, if the diode is reverse biased, what happens? If the diode is reverse biased, right? If the diode is terminals are reverse means diode is reverse biased. Then resistance becomes infinity. Then no current is going to flow through the diode. Then this 2 ohms is not working, not relevant because no current flows through it. Then in the circuit, these 2 resistors are remaining. In the circuit, these 2 resistors are remaining. Which 2? These 2. 2 ohms and 2 ohms. Then 2 means 4. Right? 2 means 4. Now, when resistors are equal, no need to apply the potential divider again. If resistances are equal in series combination, always potentials are also equal, right? If resistances are equal, then it reads 9 because 18 should be divided into 2, right? V equals 18 over, right? 2 plus 2 times 2. This is 9 volts, right? Don't check if the resistances are equal, right? 9 volts. 10. 10. A PN junction is connected to a battery as shown in the figure. When light is shown on the junction, electron hole pairs are created due to absorption of photons. The current in the circuit produced by the incident light is right? Current produced is always from now you can check the battery also, right? You can check the battery also, right? That is connected as P to N. If that is connected as P to N, current is going to flow in the opposite direction, right? Current is going to flow in the opposite direction, right? Leakage current actually, right? Leakage current. That's a leakage current. So the leakage current flows in the opposite direction. Leakage current flows in the opposite direction, right? Then if a current flows in the circuit, right, that current flows in this direction. No, make a leakage current. This leakage current flows in this direction, right? Then if the leakage current flows that way, the direction of electrons is P to N. Then due to electrons moving in the direction of P to N and holes moving in the opposite direction, yeah. So it's 2. It's 2, right? Yang current direction check right? And this functionality is very much similar to functionality of a photodiode, right? Photodiodes are always working at reverse bias, right? Photodiodes are always working at reverse bias, right? So this is similar to a reverse bias photodiode, right? 11. In the figure shown, A is a torch bulb, B and C are light emitting diodes. If a strong bar magnet is moved up and down continuously at a high rate through the coil and generates a voltage of peak amplitude 4 volts, right? Then A will go, B will go. Okay. Now we know from magnetic induction, when the magnet is taken up and down from magnetic induction, directions of current generates are opposite. No, directions are opposite, which means the current is going to change directions, right? Current is going to change directions. Now for my is, let's assume this as x, and when x is plus, right? If x is plus, A is going to glow, right? Check if x is plus, right? If x is plus, A is going to glow, right? B is also forward bias, B is also going to glow, right? B is also forward bias, B is also going to glow, right? And about C, right? Now this bridge circuit is coming from full wave rectifier, right? Make a theory part. Bridge circuit is coming from full wave rectifier. In the full wave rectifier, we know when x is plus, right, current flows in this direction. Current flows in this direction. But for this current, this diode is reverse biased. So C is not going to function. Right? Now, if you check when x is minus, the filament bulbs are working either way because they don't have plus and minus terminals. Then A is definitely working. And B is now reverse biased. B is not working if x is negative, right? And even though if x is positive or negative, current flow through the load resistor or current flow through the bridge circuit is going to be same, right? That is coming from the full wave rectifier. Check load resistor current downwards, right? It may downwards and current but for both instances, C is reverse biased. Then C is not going to function. Then the question is, right? Glowing ones, no? Both A and B glows, right? Both A and B glow somehow, but C is not glowing at any of the instances. Then only A and B will glow, right? B instance glow, B is glowing at least in one instance, right? B is glowing at least in one instance. So B glows. 12. In the circuit shown in the figure A, as supply voltage V increases linearly with time t, as shown in figure. Figure B, at time t equals t naught, supply voltage surpasses the breakdown voltage of the Zener diode. The variation of the voltage VR across 100 ohm resistor and the voltage VZ across the Zener diode. Okay, first thing, until the Zener voltage is obtained, Zener diode won't function, right? If Zener diode is not function, no current flows in the circuit, right? Until the Zener voltage is reached, Zener diode won't function, right? Then up until the Zener voltage, VR should be 0, no? Up until the Zener voltage, VR should be 0. In second one, VR is 0, right? And in fifth one also, VR is 0 up until the Zener voltage, right? Now, I have already removed 1, 3 and 4, and I have the tie between 1 and 5. I have the tie between 1 and 5, right? I have the tie between 1 and 5. Okay, then once the Zener voltage is reached, Zener voltage is constant. Zener voltage is constant. Now in both 2 and 5, Zener voltage is also constant, right? Now, up until the Zener diode functions, the potential difference across Zener diode is non-zero. Sorry, up until the Zener diode is functioned, there's a potential difference, right? Even though there's no current flows through Zener diode, there's a potential difference across, no? Then it cannot be 0. Then there's a potential difference across Zener diode, right? Until it functions. Zener diode, right? Zener diode is like this. 1 second. Zener diode is like this, right? Then across the Zener diode, the potential difference is there. So it is 2. It is definitely 2. Right? It is 2. Right? 13. In the circuit shown, R1, R2, and R3 are of the order in few kilo ohms. Appreciable currents can be found. Okay. Then let's assume this is not given, but let's assume these diodes are silicon. Let's assume these diodes are silicon. Right. Then if they are silicon, right? Now here this is -3 to -5 current flows, no? -3 to -5 current flows. Then this diode will be forward biased, right? -3 to -5 current flows. This diode will be forward biased, right? And across this diode, there will be a potential of 0.7 if that is silicon, right? And from 0 to -5 also, right? May direction current flow, no? May direction flow way, right? And from 0 to -5 also, there's a potential difference, no? Then current flows, right? Then current flows this way current flows. And if this potential difference is 0.7, right? If this potential difference is 0.7, right? 0.7, then this is going to be what's the value? After හරියට මොන value එක හොයාගන්න පුළුවන්. This is going to be -5.7 no? -5.7 no? Sorry, this is going to be -4.3 no? Right, මෙහෙම වෙන්න ඕන. -4.3. This is going to be -4.3, right? හරි, දැන් නිකන් check කරලා බලන්න. Now this is from, let me use a different color. See, this is from 0 to -4.3. Then current flows. Then this is from -3 to -4.3, that is greater than 0.7. So a current flows, right? There's a current flows, right? And this is from 0 to 4.3, right? The current flows. Then appreciable currents can be found. R1, R2, and R3 all, right? But in the exam, there was a confusion about these potential differences with the value of the resistors. Resistor එකේ value එක වෙනස් වුණොත් පොඩි change එකක් වෙන්න පුළුවන් නේ. Then in the exam for both 3 and 4 marks were given. It was given as both 3 and 4. But if we argue this way, the answer is 4. And if you argue this way, the answer is 4. But in the exam, both 3 and 4 were given as answers, right? 14, right? See, 14 is a good one. If the voltage necessary to forward bias the diode shown in figure is 0.7, the current in the battery. Okay, then let's assume this point is x. If this is x, this is also x, this is also x, right? If this is x, this is also x, right? And when current flows this way, right? May have current flow and right when this current flows this way, right? This point is say that is y. This y is Vx minus IR, no? Right? That y is Vx minus IR, which means potential at y is definitely less than potential at x. Potential at y is definitely less than potential at x. Now the problem is this, right? The diode is connected like this, right? This is Vy, this is Vx, but Vy is less. If Vy is less, this diode is reverse biased. If the diode is reverse biased, resistance is infinity. Resistance is infinity. No current is going to flow through this diode. No current is going to flow through this diode, right? No current is going to flow through this diode. Then, if no current flows through that diode, can you see that these two currents should be equal in that case, no? Right? These two currents, say this is simple line, then this is also simple line. Because these two currents are equal if no current flows through the diode. Which means this 1000 and 200 are in a series combination. Then there is 1200 means 1200, 1000 plus 200. And this is also 1200. This is also 1200. They are connected between same points. Can you see? Now, from the top, this 1000 and 200, this is also between X and Z, 1200. And this is also between X and Z, 1200. Then, if the resistors are connected between X and Z, right? If both resistors are connected between X and Z, 1200 each, right? The equivalent is 600 ohms. Equivalent is 600 ohms. Now we need the current from the battery now. Then apply delta V equals IR for the system. Then delta V equals IR for the system. Delta V is 6, right? We need I. R is 600, right? R is 600. Then this is 6 over 600 amperes, right? Given answers are in milliamperes, right? Then 6 over 600 is 1 over 100 no? Into 1000 milliamperes. That is 10 milliamperes, right? 10 milliamperes, it's 3. 10 milliamperes, it's 3, right? 15. Two NOT gates are these actually put by a mistake under this in the classification of phase rule, right? This should come under logic gates, no? Right? Otherwise, it should come under logic gates. Two NOT gates are connected as shown in figure. Consider the following combinations of logic levels for Q1 and Q2. Which are the above combinations will provide stable logic levels? Okay. Stable logic levels means they should not be invalid cases. They should not be invalid cases. Right. Now, if you check for Q1 0, right? Q1 0 check if Q1 is 0, right? If Q1 is 0, along this wire, this becomes 0. No? If there is 0, right? If there is 0 along this wire, right? If this NOT gate is simplified, this is going to be 1. This is going to be 1. But from here, if you simplify this, right? If this is 0, right? If this is 0, now when you simplify this, this is also 1, this is also 1. Okay, that is satisfied, which means now this should be logic level for Q2, maybe Q2. Which means when Q1 is 0 and Q2 is 1, that is stable, right? When Q1 is 0, and Q2 equals 1, that is stable. That is stable. Right? Then similarly, the opposite is also working now. If Q2 is 0 and Q1 is 1, that is also stable. Right? But for the cases like 0, 0, my first answer again, for the cases like 0, 0, when Q1 is 0, Q2 cannot be 0. That is invalid. That is not a stable case. When Q1 is 0, Q2 cannot be 0. Q2 cannot be 0. Why simplified? Then that is not a stable case. Then it should be 0, 1 and 1, 0. BC. Should be BC, 5. Right? It should be BC. 16. In the circuit shown, D is a silicon diode. The voltage source provides a variable voltage V. Which of the following curves best represents the variation of I with V? Okay. Then since there is a silicon diode, until the voltage barrier exceeds 0.7, the diode is not functioning. Right? Then from 0 to 0.7, right? From 0 to 0.7, current flows through 100 ohms. Right? 0 to 0.7, current flows through 100 ohms. Current flows through 100 ohms. So that is not 0 until 0.7 because current flows through 100. Right? That is not 0 until 0.7. No? That is not 0 until 0.7. It flows through 100. So that is non-zero. Then in the third case, there has been 0. No? 3 vagega kwenna there. Then after 0.7, when V is greater than 0.7, right? What happens is diode is forward biased. when the diode is forward biased, diode functions. Then hereafter, that is IV of a diode. IV of a diode is this, no? IV of a diode is this. Right? IV of a diode is this. IV of a diode is this. After that point, it should follow the IV of a diode. Right? It should follow the IV of a diode. Then we have two and 5 remaining now. In 5, that is a curve. In 5, there is a curve, right? Now, since the what we call the resistor is also working, right? Since the resistor is also working, now there's one more thing to think. Right? Resistor works from delta V equals IR, no? Delta V equals IR. When the resistor works, this is a line. This is a straight line. Line goes through center. That is a center. That's a line. That's a curve. That's a straight line. Goes through origin. Right? Then since the what we call the resistor is also working, it should have a linear variation after that point, because resistor is still working. So that cannot be a curve. Just as a diode, resistor is also working, so it has the linear property. So it is 2. Right? What do you thinking? That's a small thinking out of the box. Right? 17. The circuit shown in the figure is made of ideal elements. When the sinusoidal voltage of peak amplitude 5 volts is applied to the input, the waveform of the output voltage we want would be. The theory part coming from here is from the half wave rectifier. Right? This is coming from the half wave rectifier. Right? That is coming from the half wave rectifier. Then this is now plus and minus, no? When this is plus, what happens is, right? When plus, D will be forward biased. Right? When D is forward biased, this functions. When D is forward biased, this functions, and right, there's V out. But when this is minus, D is reverse biased. When this is reverse biased, now when this is forward biased, the capacitor charges, no? Right? Now in this case, capacitor charges, right? But in this case, no V out, right? No V out. Then capacitor discharges. When capacitor discharges, it gives a it gives a charge to the circuit. Then circuit is connected like this. Right? Half wave rectifier now if you know these things, see how easily you could do. Right? What capacitor does is something like this. Right? Now that same phenomenon, what we call the functionality of the capacitor should be here. So it is 2. Right? It is 2. Right? Now in this case, a very small time period is considered, so it is given as kind of a constant one, because that's a small time period. Right? Otherwise, this is how a capacitor functions. Right? The idea is coming from half wave rectifier. Right? It is coming from half wave rectifier. 18. The box P shown contains a circuit 10. When a battery is connected between A and B, the light emitting diode LED connected to the circuit is lit. When the following circuit, which of the following circuits inside the box P enable the light emitting diode to be lit even the battery terminals are interchanged. Okay. Now let's assume as A is plus, right? If A is plus, see what happens. If A is plus, this diode is going to forward biased. If A is plus, this diode is going to forward biased, right? And if A is plus, C is going to be if A is plus, C is plus, because current flows through this. If B is minus, D is minus, because current flows through this, right? Then if this is switched, right? If this is switch right? Now in this case, if A is plus, this diode is forward biased and D becomes plus. If B is plus, the diagonal diode becomes forward biased and this becomes minus, right? On a case. And in this case, if this is plus, A is plus, this horizontal diode becomes forward, then C becomes plus. If B is minus, right? Then the horizontal diode becomes forward biased again, -2. This one is negative, is connected now. Then that becomes forward biased, and D becomes minus. D becomes minus. Right? Right? Then, oh, 1 second. Wait. About the second one. A plus negative, A plus can may forward do not. This becomes plus. Sorry. If B is minus, this is going to be reverse biased. Reverse biased. And D is minus. I think about short circuit case. If A is plus, only 0.7 of A is dropped, and this becomes this. Okay. Yeah. Then in this case, it is like both plus and minus are going to get to the same terminal. And C is not going to get any voltage because from both A and B, the diodes are reverse biased. These two are reverse biased. From both A and B, these two are reverse biased. Right? So razor get a common function. Okay. Then when the terminals are switched, right? I check if A is minus, right? No diodes are here, this becomes minus. If B is plus, no diodes are here, this becomes plus. Right? Now plus and minus changes, then this LED is not going to function. If plus minus changes, LED is not going to function. So X is not a suitable circuit. Right? Now in this case, if this becomes minus, right? This is reverse biased, and this is going to get a minus charge. And if this is plus, this is going to be forward biased, and this is going to get a plus charge. Right? Now that's a malfunctioning circuit because not C and D are not going to get plus and minus. There is only C or D that is not going to function as a circuit. Right? In this case, if A is minus, this diode is forward biased. Then this becomes minus again. Right? If B is plus, this diode is forward biased, and this becomes plus again. That current. Now about C, in both cases, plus minus of C and D remains unchanged. Then C is going to function in this circuit, right? C is going to function in this circuit if it is giving same output means if LED is lit in both cases, right? What is the argument? 19. Breakdown voltage of the center diode in the circuit is 5 volts, right? Center diode is 5 volts. RL is a suitable resistor. The capacitor C is first charged to 10 volts by closing the switch S1. Okay, when S1 is closed, right? Closing the switch S1 and open S2, right? Then capacitor is charged from this, no? We know for a capacitor Q equals CV, right? For a capacitor Q equals CV. Then when the potential difference is given, capacitor is charged, right? And it stores a charge. Subsequently, S1 is open and S2 is closed, right? Now S2 is closed. Consider the following statements made about the functioning of the circuit after S2 is closed. A. Voltage across RL will be 5 volts so long as the capacitor voltage is adequately above 5 volts. Definitely, because if capacitor's voltage is above 5 volts, center diode functions. Right, always, center diode is going to keep center voltage across the center diode, that is VC. And center diode and load resistor are in a parallel combination, no? So that is same. Then if the capacitor has a voltage greater than 5, that is always correct. If that is less than 5, center diode won't function. Time period through which the voltage across RL remains constant does not depend on the value of the capacitance. Wrong, no? Because higher the capacitance, higher the charge it can store. Higher the capacitance, higher the charge it can store. Right? Higher charge is stored means higher the time it takes to discharge. So that is wrong. Potential drop across R gradually decreases with time. That is correct because capacitor always decreases over time. Then A and C are correct. It's 4. Right? A and C are correct. It's 4. Right? A and C are correct. It's 4. 20. In the circuit shown, each of the rectifier diodes requires a voltage of 1 volt across it to make it forward biased. In order to make both diodes forward biased, the voltage of the battery X should be. Okay. Now, this is a common terminal, no? Right? This is common. If this is X. Right? Then, if you need a potential difference of 1 across these two, right? These two. Now, potential difference from X to this point is now 3 volts, no? x to this is 3. Now just check what happens if this is 4. You can check kalaba. If this is 4, potential difference across this diode is 4 minus 3, 1 volt. That is fine. Potential difference across this diode is 5 minus 4, right? 5 minus 4, that is also 1 volt. That is also 1 volt. Since x is a common terminal, we can easily compare. Since x is a common terminal, right? X is a common terminal. Take easily check karaganna puluwa. X is a common terminal, right? When a common terminal is given, when you are giving the questions, right? Even if you assume this as a grounding, that is totally fine. That is totally fine. You can just assume that is not a grounding, that we don't know. But even if you assume that as a grounding, in terms of potentials, that is not going to do any potential differences. In terms of potential differences, that is not going to do any change, right? I think another 5, 4, 4, 3. Then the battery should be 4 volts. Battery should be 4 volts. Right? Grounding right? If you assume that as a grounding, when you find potential differences, that doesn't matter. 21. The waveform shown in the figure is applied across the input terminals AB of the circuits P and Q. Sorry, circuit PQR. So PQRS, 4 circuits are given. Okay. Then question: if the potential drops across the diodes are negligible, which means they are ideal diodes, the input waveform will travel unaffected through. Okay, which means it should be unaffected. It should be same. It should be same in both cases. Right? See, if you check in the first one, right? Then make me plus minus change and check karagan. Now in this case is plus minus changes. Plus minus changes. Then check what happens when A is plus. See, when A is plus, right? Even though this diode is forward biased, this diode is reverse biased, then that is not going to get any output even, right? So P is not going to work. P is not going to work. P is not going to work, right? In the second one, when A is plus, this is forward biased, that is functioning. But what if A is minus? Plus minus changes, no? When A is minus, both are reverse biased, then the signal is harmed. Both are reverse biased means no output. Signal is harmed. Then R. If A is plus, this diode is forward biased, and this becomes plus, the output is coming. And if A is minus, this diode is forward biased. No? If A is minus, this diode is forward biased, and again the minus potential is coming out from that end, then that is unharmed. Then R is correct. In both cases, it gives the same output. In both cases, it gives the same output, right? In both cases, it gives the same output, right? Then next one, if A is plus, this is going to be forward biased. If this is forward biased, right, this will be plus, right? Right? And now what has happened to the signal? Signal has inverted, right? A වලින් දුන්න signal එකේ plus එක එන්නේ මෙතන ඉන්නේ. That is inverted. If the signal is inverted, which means still the signal is harmed. And this is also not a possible scenario because here signal is inverted. Then it should be only R. It should be only R. Should be only R. 22. Right. When the switch S is closed in the circuit shown, only A will glow. Okay. This is closed now. Right. This is closed. Right. Check forward and reverse diodes. That's it. If a diode is forward bias only, a current flows through it. Right. Now this is positive plus. And if there is plus, right, for that plus current, this diode is reverse bias. No, it is not going to function. Which means D is not going to function. Reverse bias diode, no current flows through reverse bias diode. Right. Then if this is plus, this diode is reverse biased, but this is forward biased. Then current flows through this, C is going to light up. Because current flows through C. That's a forward biased diode. Then here, this is plus, this diode is forward, all these diodes are forward. So current flows through B, it is lighting up. And here, this is plus, these diodes are going to forward bias, but this one is reverse. No current flows through the reverse bias diode. Then no current flows through A. A is not lighting up. Then only B and C lights up. It is 2. Only B and C lights up. That is 2. Right? 23. Which of the following is not a source of EMF? Right. So what we consider a source as, what we consider as a source is actually, right, if something can generate its own electromotive force, that is called a source. Huh? Because this confusion comes with the capacitors, because capacitors can store charges and release charges, no? Right? This confusion comes with the capacitors. Capacitors can store charges and release charges, but we have to charge the capacitor externally. We have to charge the capacitor externally. So that is not an own charge by the capacitor. That is not an own charge by the capacitor. What capacitor releases is an external charge that we have given to the capacitor when charging. Right? That is an external charge we have given to the capacitor before. So therefore, capacitors are not considered as a source of electromotive force. Right? Electrochemical cells, you know, photodiodes, you know, photodiodes, when light falls to photodiodes, right, it generates EMF, it generates EMF and current. We discussed in photodiodes. And the third one, piezoelectric crystal means, right, that's a specific type of substance. When it is squeezed, when that is squeezed, right, it can generate EMF, right? Simply, when it is squeezed means when a stress is given. When a stress is given, this can produce. So this is also correct. Thermocouple is correct. Thermocouple is correct. Right? Charge capacitor is the answer here. The confusion, if you are confused with the capacitor, the point is that capacitors don't have its own charges. Capacitors don't have its own charges. That's an external charge. Okay, 24. In the circuit shown, X and Y represent the terminals of a variable voltage source situated in the box with broken lines. P is a variable resistor. D is an ideal diode. As the value of voltage Vx at point X is gradually increased from 0 to 15. Gradually increased from 0 to 15. Vx is here. Vx is increased from 0 to 15. Which of the following graphs correctly represents the variation of the overall resistance R of the section of the circuit right to XY? Okay. Right. Then initially, if you check when it is 0, right? When 0 කියන instance එක check කරන්න. When Vx equals 0. See what happens? When Vx equals 0, right? Now, this is a ground in. This point is 0. This is a ground in. No? This is a ground in. This is 0. Then this end is at 5 volts. Right? This terminal is at this end is at 5 volts always. Right? This point is at 5 volts. Right? මේක තියෙන 5 volts වල. මේක හරිනේ. Right? Now, if Vx is 0, right? Now this side is 0, something like this. Now, across 5 and 0, the diode has got an enough potential difference to forward bias the diode, right? It has got an enough potential difference to forward bias the diode. If the diode is forward biased, right, we know if the diode is forward biased, resistance of the diode becomes 0, right? If the resistance of the diode is 0, right, equivalent resistance of these two becomes 0. Then equivalent of this circuit is 1 kilo ohm. Equivalent of the circuit becomes 1 kilo ohm. Right? අරක 0 වෙන්න කොහොමද කියලා මම කලිනුත් කිව්වා. 1 over R equals 1 over 1 plus 1 over 0. 1 over 0 is infinity. Then 1 over R equals infinity. Then R equals 1 over infinity. 1 over infinity is 0. Right? Now, total resistance of the system is the remaining 1 kilo ohm. There is 1 here. Remaining 1 kilo ohms here. Then when there is 5, it should be 1 kilo ohms. When there is 0, it should be, how many? 1 kilo ohms. When there is 0, it is 1 kilo ohms. Then from these answers, this is wrong because initially that is 1. No? Then this is also wrong, right? This is also wrong. Now, from that first thing, I have only 2 answers remaining, right? From that very first thing, I have only 2 answers remaining. Right, then you better check with the other end. Right, මොනවද අපිට තියෙන doubts and 2 එකයි 4 එකයිනේ. Alright. 5 කියන point එකේ තියෙන check කරන්න වෙනවා. At 5 what happens? Right, exactly at 5 what happens is, right, at 5 when Vx equals 5, right, I'll be erasing this. When Vx equals 5, See, when Vx equals 5, now this becomes 5. 5 minus 5 means there's no enough potential to forward bias the diode. 5 minus 5, because the required potential difference that should be there is 0.7 to forward bias this diode. Right? If there is a silicon diode, that is 0.7. Now 5 minus 5 means there's no potential difference, potential drop from here to here in the circuit. Then diode is reverse biased. If the diode is reverse biased, resistance is infinity. If the resistance is infinity, no current is going to go through the infinite resistor, then current flows through these two like this. Then 1 and 1 means resistance becomes 2. Resistance becomes 2 just after 5 volts. Resistance becomes 2 just after 5 volts, just after 5, right? Which means only possible answer is 2. Only possible answer is 2, right? 5 වලින් පස්සේ 2 කියන resistance එකට යන්න ඕන. Because diode is reverse biased. 25. A diode and a resistor are connected in such a way that only two terminals are available for external connections. When the voltage of 1 volt is applied across the external terminals, the current through the circuit is 50 milliamperes. When the applied voltage is reversed, the current doubles. Okay, if current doubles, resistance should be halved, no? Resistance should be halved. Then if the resistance is halved in the next case, which means that is because of the diode, no? Which means diode should be forward bias in the next case. Then only it can be halved, right? Forward or reverse. And these two should be in a parallel combination in that case, no? Right? නැත්නම් forward reverse මාරු වෙන්න බෑනේ. Right? මම නිකන් හිතනවා මේ දෙක මේ වගේ ඇති. Right? Something like this should be here. Right? Something like this should be here. Right? Now, if this was, right, one argument again. If this was positive, if this was positive and this is negative, this diode is reverse biased. Diode is reverse biased. If diode is reverse biased, no current flows through the diode. Then the current flows through the resistor only. Then in that case, current flows through the resistor only. Let's assume this current as R. Let's assume the current as R, right? And the current is now given, no? Current is now given. And before doing any calculation, if I check the diagram again, after reversing this, see, if this is reversed, what happens? Right? Applied voltage is reversed. If this is reversed, this becomes plus. When there is plus, this is forward biased. If there is forward bias, this is going to be activated. Then, if there is activated, current flows through both in that case. Right? Now, resistance of diode is asked. Then you can't assume the resistance of diode as 0 now because there is asked. There is asked because there is non-zero. There is asked because there is non-zero. ඒක තේරෙනවනේ. නැත්නම් resistance එක ගන්න නැහැනේ. හරි. එතකොට ඒකත් forward වුණොත් RR two resistances are going to be working as two parallel resistors. Then resistance decreases and current increases. Right? When the applied voltage is reversed, current doubles. Then that is satisfied. So these are possible circuit. දැන් අපි calculation එක කරමු. Right now, initially, right? We know delta V equals IR. Delta V equals IR. Then delta V is 1 volt. I is 50 milliamperes. 50 10 to the minus 3 R. Then R equals 10 to the minus 3 means 1000 here. 1000 no 50. That is 20 ohms. Then resistance here is 20 ohms. If the resistance of the diode is resistor is 20 ohms, and if the resistance of diode is also 20, right? When they are in reverse condition, right? Reverse means when the EMF is reverse, diode is forward. Then if they were 20 and 20 both, 1 over 20 plus 1 over 20 becomes 1 over 10. Then resistance is halved, then current doubles. Then definitely it should be 20 and 20. Right? 20 kilo හොයාගත්ත නම් ඔයාලා try එක තියෙන්නේ මොනවද? 20 10 20 0 20 20. Current is doubled. To double the current, resistance is halved. To halve the resistance, it should be 20 and 20. Right? 20 20 parallel means 10. Right? That's a creative question. Right? That's a creative question. Okay. So that's it about semiconductor diodes. That's it about semiconductor diodes. Right? I'll be publishing the other parts of the electronics also as videos, as recorded videos in the next days. Right? All right. Then practice these questions before you go to the exam and make yourself comfortable and confident enough with these questions. Right? So I hope this would be a help before you are going to exam. Right? When you are practicing these questions before you are going to the exam. All right, then that's it. Right, see you in the next session.